So compute the shearing stress in each of the four walls of the two tubings when it is subjected to a torque of 25 kipinch. Is what it means is really that that's how the beam is, and it's subjected to a torque of 24 kipinch. Okay, so we know that the shear stress is the torque divided by 2 times the thickness times the area, and the area is essentially need to find the midline here. The area is going to be the area between the midline, as shown here. Okay, so there are two beam sections. You can see that the way they differ is they probably have different cross-sectional area A, or maybe not. We'll have to check. They also have uniform thickness on the one on top A, and the one below B has well, different thicknesses. There's 0.12 for the top and the left half, and 0.12 for the top and the left half, and 0.2 for the right and the bottom one. So clearly, because this is a function of thickness, we'll expect that the shear stress in the bottom one is not going to be the same on all the four sides. It's going to be same for A because you can see the thickness is the same. So for A, we can expect that the shear stress in AC is equal to shear stress in AB equals shear stress in BD equals shear stress in AC equals torque divided by 2 times tau times A, 2 times thickness times A. So let's go ahead and figure out what that what A is. So let me draw the beam, sort of draw an exaggerated view of the thickness, the midline. Okay, and I'm interested in computing this area. Okay, so let's compute that area. It's basically this distance and this distance, and I need to take the area of that. So for the bottom one, we have 4 inches, and then I need to subtract out half of 0.16 on the left side and half of 0.16 on the right side. So this is 4 minus 0.06, sorry, 0.08 minus 0.08. Okay, this is to account for half of the left side, half of the right side. So I think that comes out to be 3.84. And for the right one, again, we need to take 2.5, which is edge to edge, and subtract half of 0.16 and half of 0.16. So 2.5 minus 0.08 minus 0.08, that comes out to be 2.34. Okay, so you also see that the thickness of all the four sides is the same. It's 0.16. So now we can solve for this. We have the torque 214, 2 times thickness 0.16 times the cross-section area, which will be 2.34 times 3.84. Okay, when we do the math, we get the shear stress tau AC equals tau AB equals tau BD equals tau AC equals 11.13 KSI. Yeah. Oh, sure. Sure, yeah. My bad, yeah. Twice here too. AC, AC, AB, BD, and DC. Okay, let's solve part B in a similar fashion. I need to uh, again do the same thing, find the area. Maybe we should show it like this. This is the part in yellow. Okay, let's do the same thing. How we note that uh, the only difference between the top top and left and bottom and right is that the thickness is different. So 0.12 is the thickness for the those two parts and 0.2 for the right and the bottom one, which means that the since thickness shows up, those will have different stresses. So we expect that tau AB equals tau AC. So, so part B. Two times 2TA, and then we'll expect that PD and DC would have the same, but they have the same thickness, so they'll have the same stress, PD, DC. The cross-sectional area is going to be the same. So let me redraw that section with the midline. It's rather this way. I've drawn it slightly exaggerated to show that it's unequal. And now we need to figure out, we need this area. Okay, so we go back here and see that's 4 minus the left thickness is 0.12. So half of that 0.06. Right thickness is 0.2. So half is 0.1. So 4 minus 0.06 minus 0.1 comes out to be It actually comes out to be the same as before, 3.84. This was 3.84. Okay, and then the height is 2.5 minus, well, half of 0.12, again half of 0.1. Go here. 2.5 minus 0.06 minus 0.1. It actually also turns out to be the same as before. So 2.34 was the same cross-section area we got earlier. So the area remains unchanged. What will change, however, is the thickness. So thickness 0.16, sorry, 0.16 versus 0.12, 0.2. So with that, we can solve this problem. So the torque is 24 twice. Now this is the thickness of AB or AC. So AB, AC. So thickness is clearly 0.12. And then area is 2.34 times 3.84. And this one will be 24 divided by 2 times thickness is 0.2. Cross-sectional area is the same, 2.34 times 3.84. And then the answer is 8.35. Oh, my bad. I don't have error here. This is not 11.13. This should be 8.35. My bad. I just correct this. This is 11.13. And this one is 6.68. One. See, what we note is that this has the highest stress, 11.13. This one is 8.35. So this is the minimum stress. The highest stress occurs where the thickness is the minimum. And then the least stress, which is this one, occurs where thickness is maximum. So higher the thickness, the lesser the shear stress. However, what happens is when you increase the thickness, you increase the weight of the material. And when you increase the weight, there are other repercussions, like maybe it's used in a automobile where you have to carry that extra weight, and that's not good. So there's always a trade-off between increasing the strength and decreasing the weight. Always happens in design.